Hello, this is our final design project of machine design course for mechanical engineering. Today, we're introducing and presenting about our machine design project for studying the small wind energy systems, mini wind turbines. So first of all, today is a era of the clean energy. We see the sustainabilities and we hear about the clean energy everywhere and anywhere, anytime. However, there are some cases that the people cannot access to the electricities until today. Like in some remote areas, it can be difficult to access the on-grid power distributed by the government, or only reliant on the solar power. The solar panels obviously don't work on the nights or the cloudy days where the sunshine is not available. The worst case is that one we reliant on the fewer power generator to get the electricity. In some cases, when we don't get the sufficient power, it can be so harmful to the environment as it can leave the ecological footprint to the environment and the carbon footprint also. So there is another possible solutions came to our community, which is a wind turbines. Here we see the populations who cannot access the electricity. We can see until 2023, there are over the half a billion people in the world cannot access the electrical power from the grid lines. They're mostly from the sub-Saharan Africa, where the rural areas, like I mentioned before. So now our objective for designing the mini wind turbines is for the household or the small businesses users in the rural areas where the power grid is unavailable or the power is insufficient. We're focused only on the aerodynamic principles and mechanical principles of the wind turbine technologies existed until today, and we're not focused on the electrical control systems or any other things which are not related to the mechanical engineering. So first of all, before we design a wind turbine blade, we need to clarify that which wind turbine blade is the most efficient way to capture the mechanical energy in the winds. We see the vertical wind turbines as the A, and we see the horizontal axis wind turbines C, D, E, etc. According to our literature review, we see that the curve D is the most efficient in terms of the power, which is the three turbines, horizontal axis wind turbine. So we're gonna use the horizontal axis wind turbine with three blades in our design project. So here we see the wind speed according to the locations of Thailand. There's a based on the height of the 10 meter from above the sea level. The redder the patch, the faster the wind speed. In the Ratchasima, we see the northwestern part of the areas are the most efficient when we are installing the wind turbines. Like we see in the real world, there is some Lemtagon wind turbine projects around the points shown here. So these are the ideal place in the Ratchasima for designing a wind turbine blade and installing it. We're specifying a point of locations and the height to specify the data of the wind speed and the wind energy densities and the wind direction, etc. to proceed our process of designing a blade. Here we see the maximum rough wind speed is 3.5 meters per second and wind energy density of 74 watt per meter square. In Nagarajasima, the wind is mainly from the northwestern part or the southwestern part or the northeastern out of the region. Before we designing a turbine in the software, we need to determine the Reynolds number, which is crucial for optimizing the wind turbine's efficiency and capabilities. So we use a wind airfoil2.com to calculate the Reynolds number to know the Reynolds number. The chord width of the turbine blade is based on the average chord length of the entire blade, which we set around 10 centimeter, and the kinematic viscosity of the air at 30 degrees Celsius, which is close to the local temperature, is around 1.5 10 to the minus 5 meters squared per second, and we got the Reynolds numbers around 23,000, which is far less than the critical Reynolds number over a flat plate, which is 500,000. So we can say that this is a laminar regime. We will use a standard airfoil, which is knockout 4412. According to our literature review, the knockout 4412 airfoil is the highest lift to drag coefficient ratio among the other airfoil, where we typically use in a small wind energy systems. So in our software, when we calculated the angle of attack versus the coefficient of lift to drag ratio, we see that the maximum lift to drag ratio is 5.32 around the angle of attack of 6.5 degrees. At the tip ratio 7, it is around 235 RPMs, which is um, roughly close to the actual small wind turbines RPMs at the Reynolds number 23,000, which we get before. So we will use the Qblade wind turbine simulation software, and we finally get the wind turbines as shown here. We will set the wind turbine blades from the 0 to the 1 meter, and we got the rotor diameter of 2.1 meter and the area of 3.46 meters squared. Before proceeding to the other parts, I'd like to introduce about the wind energy from the steady wind. According to the rotary actuator Dick's theory, the wind from the wind energy is according to these equations, half rho a velocity to the cubes. So according to our wind energy, energy velocity and the sub area will get 85.659 watt. And there's another law relating to the wind energy. According to the best law, it is that the possible maximum power from the rotor can be 59.3. No wind turbine systems in the world can exceed the maximum power estimated by the Betz law. So according to the Betz law, our maximum power extracted can be 50.8 watts for round set. And we proceeded to the steady BEM simulations, which is a blade element momentum method. And according to our airfoil, we see that at the tip speed ratio of 5, our power is approach to the 34 or 35 watt and the collective pitch angle 8.5 degrees, which is we got the maximum efficiency of our wind turbine is 40.5%, and it is the 68.38% of the best limit, which is we can say quite efficient for a wind energy, small wind energy systems. For further technical review, we see that the axial induction factor is 0.1357 we got, while the optimum value is around one third, 0.33, etc. So based on this result, we can say that our wind turbine is quite efficient compared to the market today. So this is a structure analysis of our wind turbines. We see the sun stresses distributed across the wind turbine blades. We have the two main load types, which is a tension loading on the lift force causing on the turbines where the forces cause the rotor to rotate, which is we can say torque. And another loading is a normal loading where the drag force causes the blade to have the bending moment. We can imagine that in the wind turbines. So after the structural analysis, we will continue to the part of the designing the wind turbine blade in the 3D CAD software, where my teammates will continue to explain the part.
So for our project, we also have an AutoCAD design that we have been building. First of all, I would like to talk about is the nacelle, which is the main body of our wind turbine that put a lot of steps such as like shaft and gearbox if you want to. So let's talk about it. So first of all, I would like to talk about its location. So nacelle in wind turbines are generally sits on the top of the tower, and it's usually behind the blades because it holds the blade roll and rotor. And its function is, as I said before, it houses all the essential components and that can convert mechanical energy from the rotating blades into electrical energy, things like shaft and gearbox. And for the next one, I'd like to talk about is the rotor. So the rotor is positioned at the front of our wind turbine, and it includes the blade and the head, which are the essential for our wind turbines. And its function is responsible for capturing kinetic energy from the wind and also converts that energy into rotational mechanical energy to drive the whole turbine operation, which is necessary. And next thing I would like to talk about is the base. The base for the wind turbine is unnecessary because it holds a lot of load from not only from the wind turbine itself, but also from the coming winds. So as the location, it is the base and the foundation located at the bottom of the wind turbine, and it's anchoring the entire structure from the ground. And like I said, its functions are ensure stability and safety for the wind turbine, and it supports the overall weight of the turbines. Next is going to be our tail vane. So that tail vane is attached to the rear of the rotor on the wind turbine. And its function is helps to orientate the turbine to face into wind for optimal energy capture, because without this wind turbine cannot turn or tend to the desired or tend to the directions that has a lot of winds coming from. And it also provides stability during high winds and ensuring the consistent operation throughout his whole life, whole experience life. So for the next thing, it's gonna be the mast. So you can see this is a tower. So for our design, we decided to make into two parts. First is the upper mast and the another is the lower mast. I'll explain later. For the upper mast, is the section above the midpoint of our tower, and its function is hold the nacelles and the rotor, supporting the operation components from the wind turbine, and it is kind of like adjustable that we can move and we can make our wind turbine height adjustable. So next one is lower mast. We can adjust it. As I said before, we can make it suitable for a desired locations. And that section is below the midpoint of the tower, and its function is provide structural support and stability, and also helps to anchor the turbine to the foundations. So this is our overall designs of the AutoCAD design of our wind turbines, and the blades are made of fiber reinforced polymer, which are good for strength and durability. And as we can see, the wind turbine is quite fascinating, and it includes all the key components such as blade, nacelles, tower, and tails, which are necessary for our wind turbine design perfect. So let's move to our next part, which is the selections of electric generator. For this part, it is quite complicated because we have to consider factors such as like active, reactive power levels, like features. We need to also think about the voltage tolerance, frequency, speed, and also output power. Like there are a lot of factors that we need to consider to choose the electric generator. So we decided to this electric generator to be like customer choice, because we cannot give the proper we cannot find the proper electric generators. So like in the quote, therefore selecting and deciding the generator is a highly technical decisions. Viability studies should be conducted. So this is from the book, from the chapter 7, small wind energy system, from Marcelo, I think so. Yeah, so for our case, we do need a lot of calculations and a lot of data in order to make our generator efficient. So we decided not to put a specific generator in here because it varies according to the desired our power outputs. So our general idea of powering turbine is simple. We will use our wind turbine to collect the wind energy from the wind turbine in the dry battery, and we will use the stored energy to power the electronic devices such as lamps, fans, or even smartphones. We can use whatever we want with this energy we got from our wind turbines. So we will move to the next to the ends of our presentation, which is the factor consider break-even point. So in order to achieve maximum efficiency of our wind turbine, wind speed is the most important thing. So a small increase in wind speed also can result in a large increase in power. So I would like to recommend is putting by using a high tower can increase the productivity of our wind turbine, and also giving access to higher wind speed, which can lead us to more power generations. So for our case, like using in Nakon Ratchasima, especially in SUD, I would like to recommend is to use in tall building, such as like a digital tech lab building, which are very quite tall. So we can put these wind turbine at the top of that buildings, and we can just forget about the consideration of higher tower, because that buildings is gonna be added as a tower for our wind turbines. So this is gonna how we can implement this our wind turbine in this SUD university campus. And also we can also consider about the initial costs, such as like building the turbine infrastructure costs, regulatory fee, which are also quite sufficient. And I believe these costs will depend on the customer choice, like which place are we going to use this wind turbine? Are we going to use in very high scale, like high scale production zones, or I will just use these wind turbine for households? So it is just a variable. It's just a variable, so it depends. It depends on the customer demand. The price will be go up and down. So for the operational cost, so of course, wind turbine is also a machine. We need to maintain. We need to monitor. So these costs will also have to consider. And the last one is expected lifetime of our turbine. Is like most of the wind turbine can last quite long. So I expect that from that is that our like wind turbine can give great efficiency, productivity and give the enough energy to give our households and everywhere we want to use. So this is our reference that these research data that we use for our presentations. And thank you for your attention, Ajahn.